Okay, hello everyone. Welcome to the 10th lecture in ECE 560. Before we get started, if you have questions or comments, let me know. So this is lecture number 10. And last time we started our discussions on the linear quadratic regulator, also called an LQR. So the linear quadratic problem is a problem which comprises of a linear system. So that's where it gets the name linear. And we formulate a cost function which is quadratic in terms of the state and the input. So this linear comes from the fact that the system dynamics are linear. Okay, and the quadratic is coming from the cost function. So if you remember, we defined a cost function over a time horizon in the form of an integral, and the structure of the cost function was a quadratic form of the state vector and the input vector. So this is the cost function. All right, so we call this an LQR, and last time we saw how we can derive it. So I'm just going to give you a summary here before we can see more details and examples on LQR. So like other controllers that we saw in this course, it is really a feedback controller. Okay, so when I say feedback controller, again, it is of the form u equals to minus k of t x of t. Okay, so important to note here that this controller is dynamic. So this is a dynamic gain vector, as opposed to the static gains that we have been seeing earlier in the linear state feedback controller. So this LQR controller, again, assuming perfect state information, is of the form u equals to minus k of t x of t, but with the added constraint that it has to minimize a cost function. Okay, so which minimizes the cost function j, and j is an integral from t to tf x of t transpose q x of t plus u of t transpose times r times u of t, and then dt. So that's the cost function, and we want to make sure that our u, which is of the form minus k times x, minimizes this cost function. So eventual goal is to find a gain vector k that minimizes the cost function. So we last time also derived that gain. So we said that the optimal gain k has a specific form, right? So that k of t can be computed as k hat equals R inverse B transpose and M hat. Right, so if you remember, this was the eventual result of the LQR controller. And this M hat is actually a solution of another differential equation that we call the Riccati differential equation. So where M hat is the solution to the differential Riccati equation. And sometimes in literature, people also refer to it as DRE. So the differential Riccati equation. Now, that equation can actually be written as M hat dot equals M hat times A plus A transpose times M hat minus M hat B times R inverse, then B transpose, and again M hat plus Q. So that's the form of the differential equation, but it has also a boundary condition which is M at TF and TF equals 0. Okay, so remember, this is a differential equation, and to solve a differential equation, you will need some boundary conditions, right? Either an initial condition or a final condition. So in this case, the final condition is given to you. Now note that this is not a very standard differential equation. It is really a matrix differential equation. Right, so the variables involved here are matrices, and it's really difficult to solve these type of equations by hand. Right, so it's a matrix differential equation. So what we can do generally is to make use of some computational solvers like MATLAB or COMSOL or many other available solvers to solve these type of equations. Okay, so generally we can use a computational solver to obtain the solution to the matrix differential equation. So the solution for M hat will be a matrix of numbers, and that matrix can be then used in finding the optimal gain vector K. Matrix differential equation. All right, so now this is really the general LQR problem with a cost function defined from T to TF, but there are also some special cases, and one special case is called a infinite horizon LQR problem. Okay, so the good thing about this special case is that you may be able to solve the Riccati equation by hand, and I will show you how that works. So a special case of LQR is called an infinite horizon. LQR, and really what this means is that the TF goes to infinity, right? So so if I want to write the cost function in that case, then the cost function becomes an integral from t to infinity. So here's the change. Okay, so instead of having a finite time as the upper limit of the integral, you will have an integral from t to infinity, and the rest is similar. X transpose qx plus u transpose ru, and then you have a d tau, because the because the t is a limit of the integral. Let me just verify whether yeah, so I think I made a mistake here. So everything here will be tau, because that's a dummy variable. Okay, so t is here. And generally it is integral from t to tf, and if you make tf to go to infinity, that becomes a infinite horizon LQR problem. All right, so if we have this type of cost function, so let's call this a x transpose mx, or let's say m bar x, then the optimal, so optimal controller in this case will be u equals to minus k bar x, where the k bar equals R inverse B transpose M bar. Okay, and this M bar is now a solution to an algebraic Riccati equation. So M bar is the solution to an algebraic Riccati equation, or ARE. So now interesting thing is that the Riccati equation will become an algebraic equation. So there is no differential equation anymore. This equation will be 0 equals M bar A plus A transpose M bar minus M bar B R inverse B transpose M bar plus Q. Okay, so this is important. And so previously we had a M hat dot or M bar dot in the beginning here. Right, so this is here a matrix of zeros. Right now, the proof of this can actually be done if you go back to your previous lecture. Okay, and you let df go to infinity. So you can actually prove that the differential Riccati equation will eventually uh, result into a algebraic one. And the good thing is that this is no more a differential equation. Okay, so this ARE is no more a differential equation, and therefore you can actually solve it even by hand. All right, so it really is a algebraic equation now. All right, so there's no derivatives. Involved. Okay, and the second thing to note is that the solution M bar is unique, and also solution is a symmetric, the symmetric positive definite matrix. A positive definite matrix. Okay, so two important things to note. Okay, so having said this, now we can go towards solving an example on an LQR problem, specifically for a infinite horizon case. So let's do an example, and that should probably clarify things a little more things that have been slightly confusing to some people since the past lecture. So we will take an example on an infinite horizon LQR. So consider a frictionless inverted pendulum with x, which is a state vector, is a combination of theta and the theta dot, and the system matrices are A equals 0, 1, omega squared, 0, and B equals 0 and 1. Now, the question is find the state, or find the feedback control law that minimizes the cost function V equals integral t to infinity theta squared tau plus u of tau squared divided by c squared d tau. Okay, so that's the problem statement. Now, first thing we have to figure out is what is the Q and the R matrices. So here we are just looking at the cost function. But from here, we have to figure out what are the Q and the R matrices, and then those can be used in the design of LQR. So by looking at the cost function, you can see that it's an integral t to infinity theta squared, right? Theta squared of tau, or let's, make it implicit here, but there's the element theta squared, and then there's u squared over c squared, and then d tau. Now, if you look at the LQR formulation, you know that this has to be an X transpose QX, and this must be a U transpose RU. So let's see how this can actually be written as something of this form. So X is a vector, and X transpose looks like theta and theta dot. Q should be a matrix, and X again is a vector, theta, theta dot. So if this product evaluates to just theta squared, then I can simply see that the matrix Q will be 1 and 0 everywhere, because this element contributes to the coefficient of theta squared. This element contributes to the coefficient of theta dot squared, and then these are the cross terms. So it's theta times theta dot. And so this is the coefficient of that term. So in this case, because our cost function is simply theta squared, so it turns out that our Q matrix is simply this matrix here. So we can say that Q is 1, 0, 0, 0. Similarly, the R matrix, we have U transpose something and then U. So in this case, because U is scalar, so the thing that lies in between is a 1/1 constant, right? It's simply a 1 over c squared, and it's a 1/1 matrix. So your R is simply 1 over c squared. Okay, so having identified R, Q and R, what we need to do next is to find out the solution to the algebraic Riccati equation. Remember, we are looking at an infinite horizon case. So we require the solution to an algebraic Riccati equation. So the equation, it can be written as 0 equals m bar A plus A transpose m bar plus, there's a minus here. So let me just verify whether I wrote a minus earlier or a plus. Yeah, so there's a minus here, right? So a minus m bar B R inverse B transpose m bar plus Q, and Q we have already identified. M bar is unknown, A is known, B is known, and R is known. So So we need to solve for m bar and then find k or k bar, which is R inverse B transpose m bar. So that's where the m will be used. Now, to find m bar, we have to, there's many ways you can do it, but one of the possibilities is to start with assuming a matrix M, which is arbitrary. So let's assume M bar to be a symmetric, that's important, symmetric and positive definite matrix. As follows. So let's say M bar equals M1, M2, and because it is symmetric, so this diagonal off diagonal terms will be the same, and then M3. Right, because here we are looking at a 2x2 system, so we can assume a M bar to be a 2x2 matrix, and let's say it is of this generic form. Remember, here these are same because of symmetric, right? So same off diagonal terms because of symmetry. Okay, so now if we start off like this, then the Riccati equation can be written as a set of algebraic equation. The Riccati equation is 0 equals ma, and then things like that. So our equation will be a zero matrix that equals m bar a. So m bar is m1, m2, m2, m3 times a. So a is 0, 1 omega squared 0 plus a transpose. So a transpose is 0, 1 omega squared 0, and same m bar. So m bar is m1, m2, m2, m3 minus m bar, which is same times b. B was 0, 1. Okay, and then R inverse. So R was simply a constant 1 over c squared. So R inverse becomes c squared here. Then we have B transpose, which will be like this. And then after that, we have M bar again. And the last thing is Q. So Q we figured out was 1, 0, 0, 0. So that's the equation we need to solve here. Now, first thing is to simplify this. Okay, so if you try to multiply things, then here what you get is m2 omega squared, and then m1, m3 omega squared, m2, plus if we simplify this, it becomes m2 omega squared, m3 omega squared, m1, m2, minus, I mean, I can simplify it quickly for you. Well, I mean, you can do it step by step. So M stays here. In the middle, what we have is a 2 by 2 matrix. And then again, the M plus 1, 0, 0, 0. Okay. Now, further simplification, this will be a, if you start adding the all the elements term by term, what you get is 2m2 omega squared plus 1, get m1 plus m3 omega squared. The same here, and then 2m2 minus, if you try to simplify this, what you will get is m2 squared, c squared, m2, m3, c squared, and then the same here. And here we have m3 squared, c squared. Okay, so that's
First, in the first matrix, first term person, it should be m2 omega square, 2m2 omega square.
what is it?
First matrix, first term.
Yeah, this one.
Yes.
No, this one is coming from here,
Okay.
right? So I will get rid of that.
Got it.
Okay. All right, let's further simplify this. So what we get is a zero matrix equals 2m2 omega squared minus m2 squared c squared plus 1. We get m1 plus m3 omega squared minus m2 m3 c squared, 2m2 minus m3 squared c squared. And here is the same as the off diagonal term. So I will just copy that here. Okay, so that's the equation we want to solve. So let's equate element by element. So by comparison, we get 3 equations. Right, so the first equation is 2m2 omega squared minus m2 squared c squared plus 1 equals 0. Then we have m1 plus m3 omega squared minus m2 m3 c squared equals 0. And the third one, because these two are the same, so we don't have to consider this again. We simply focus on these 3 distinct equations. The third one is 2m2 minus m3 square c square equals 0. So now we have 3 unknowns to figure out, m1, m2, and m3. And if we figured those out, then that's it, you found your m. So if you look at this equation is a quadratic equation in M2. Right, so you have M2 and then M2 squared and then constant. So probably what you can do is solve that quadratic equation to at least obtain the value of M2. So from these three equations, we need to solve for M1, M2, and M3. Okay, so the controller gain K bar is R inverse V transpose M bar. So R inverse is C squared, V transpose is 0, 1, M bar is something like this. So if you simplify this, essentially you get C squared, M2, M3. So luckily M1 is not even needed. Right, so note M1 is not needed to find K bar. So the good thing is you just need two variables. So from equation 1, it's a quadratic equation in terms of M2. So M2 can be solved directly. Let's first write down the equation. So the equation comes out to be minus C squared M2 squared plus 2 omega squared M2 plus 1 equals to 0. So M2 will be, I'm using the quadratic formula. So you get minus 2 omega squared plus minus square root of 4 omega 4 plus 4c squared over minus 2c squared. So M2 equals minus 2 omega squared plus minus 2 square root of omega 4 plus c squared divided by minus 2 square c squared. So eventually M2 equals omega squared plus minus square root of omega 4 plus c squared divided by c squared. Okay, so here is the solution for M2, but we only have to pick one of them. So we pick the positive one because M2 is a positive, right? Or any M2 that makes the M bar positive semi-definite. So in here we will pick positive M2 or positive solution. Because M2 is positive. Okay, so at least we found M2. Now from the other equations, there is M1 here, so we don't need to bother with this. Let's just use this equation to find the M3. So from equation 3, M3 will be the square root of 2M2 over C squared. So therefore, if you leverage your previous M2, which was M2 is actually omega squared plus omega 4 plus c squared divided by c squared. If you use this, then what you will get is 2 over c squared omega squared plus omega 4 plus c squared divided by c squared. Okay, so further simplification will give you m3 equals 1 over c squared two omega squared plus omega 4 plus c squared. So that's your m2 and m3. So therefore, the k bar is c squared m2 m3. Okay, which bracket? So yeah, okay, so what you're saying is like this? Yeah, okay, correct. So that's the m3. So k bar will be c squared, and then you have a bracket. I mean, this is the vector of k bar. So first is m2, which is omega squared. Oh, so c squared can get cancelled actually. Right, so m2 and m3 both have c squared. So the c squared outside was going to cancel the thing. So what we get is omega squared, something like this, and then a big square root 2 omega squared plus square root omega 4 plus c squared. Yeah, so that's the gain that is going to that is an optimal gain for minimizing the cost function that was described in the problem setup. Okay, so so maybe we can just encircle this. But if you look at this problem from the closed loop poles perspective, we can also see how that looks like. I mean, remember, this is an LQR, so we did not even consider where the poles would be located. But if you want to go and take that route now, the closed loop system is actually defined by A minus BK, right? So if you try to compute A minus BK, what you will get is 0, 1 minus omega 4 plus c squared minus square root of 2 omega squared plus omega 4 plus c squared, and then a square root. Right, I mean, I can make a square root on all of them. Okay, so if you want to see where the poles are, we can go to the characteristic equation. Which is determinant of SI minus A minus BK. So that will be S squared plus a big square root 2 omega squared plus omega 4 plus c squared s, and then the last term will be omega 4 plus c squared equal to 0. So if you solve this for s, basically you get the poles of the closed loop system. So solving for s, you will get S1, 2 is minus square root of 2 omega bar squared plus omega squared half, or instead of half, I can just say a square root plus minus j square root omega bar squared minus omega squared. Okay, and omega bar is actually defined as omega 4 plus c squared. So these are the poles, which are again conjugate pairs. Now we can look at what happens when. So one thing is clear, they are both in the negative half, left half, or the left half plane. So at least the controller is, or the system is stable. Now when R goes to 0, meaning when R goes to 0, what is the meaning? So we care less about energy, right? Yeah, effort or energy. So so if R goes to 0, R, remember R was 1 over c squared. So if R is going to 0, then C becomes very large. Okay, so if C becomes very large, then C is appearing here. So the omega bar squared becomes more dominant. As compared to omega squared. Right, so this term becomes large as compared to this. Then what happens is, so S12 is approximately minus square root of 2 omega bar 1 plus minus j. Right? So what has happened here is if you look at the pole, 0 plot, so you are now at a equidistant position. This may be different. Previously, it was it was not really a square. Maybe you were previously at a rectangular location with respect to the axis. But now what you've done is you move to this position, right, where the real and the imaginary values are the same. Okay. So what the other thing is, what happens when when your C decreases, so if C goes to zero, what happens?
Undefined.
No, omega square will be omega bar will be equal to omega square, right? So they are the same. So this kind of goes away. And this is like 2 times. So what you get is simply a minus 2 omega, I would say. So both S1 and S2 goes to minus 2 omega, right? And this is called the mirror image phenomenon. Okay. So that was the first example. You can also take a look at a couple more examples to understand different types of LQR controller and maybe even a higher dimensional controller where we can have more than 2 states. So a so let's think of an accelerometer example. Now, an accelerometer, let's say there's a system model which says that there is an external casing of the accelerometer. There is some mass m inside. This is the U, and this is the unknown A outside. Right, these are the forces, and so this is external case of the sensor. Now the dynamics can be, or they are probably given to you in the example, that the system dynamics are x1 dot equals x2, x2 dot equals u plus a, and if you consider if you don't consider a, then in a state space formulation, what you will have is x1 x2 dot equals 0 1 0 0, x1 x2 plus 0 1 u, and obviously this is state space considering a equals to 0. Right, so I mean, ignoring the a, which is an external input, the state space representation is provided here. Now, what the problem tells you to do is to find an LQR controller to minimize the following cost function. And so V, which is the cost function, is t to infinity x1 squared plus u squared over c squared d tau. So now without a lot of deliberation, we can easily see what is the Q and the R matrices. So here's this problem statement, but you are asked to require to also figure out what are the poles of the closed loop system. So remember previously we used to design for poles of the system. So we our design criterion was to place the poles of the system at a particular location. But when it comes to LQR, we are looking at a performance criterion. So we try to balance between the effort and the time. So we don't care much about the poles, but definitely the system or the closed loop system has some poles. And that's the second part of the question, asking you to figure out what are these poles. Okay, so first case is we can assume that A equals to 0 first. Because A is an external input to the system, so we can first solve the problem without the A, and then see how the A impacts the system. So if A is 0, basically you can say that the cost function. So from the cost function V, you can figure out what the Q and R matrices are. So what we figure out is that Q is 1, 0, 0, 0, and R is 1 over C squared. I hope by now everyone can see this from observation. So because it's x1 squared, so we are looking at only the first entity, and that has a coefficient of 1. So it's simply this matrix Q. If we also had a plus x2 squared, then we would have had another 1 here. Okay, so so if these are the Q and R, then the LQR the LQR controller will be K bar or K bar equals R inverse B transpose and M bar. So if you try to solve this, then R inverse is C squared, B transpose is again 0 and 1. And remember, M bar can be a generic matrix, M1, M2, M2, M3. So if you try to solve this again, you will get C squared, M2, M3. So the algebraic Riccati equation can be written as zero equals, I mean, I can write a full 4x4 zero matrix. 2m2 omega squared minus m2 squared c squared plus 1, and it will be m1 plus m3 omega squared. Yeah, so I am trying to actually leverage the previous calculations that we've been doing. And the previous one, the Q and R were similar. The A matrices also follow a similar structure, but with the exception that omega is 0. So let's rewrite this. There is no omega in this problem, but I was just trying to reuse the previous computations. So in this problem, we will get minus m2 square c square plus 1, and then m1 minus m2 m3 c squared. This will be the same as this. And here we get 2m2 minus m3 squared c squared. Okay, so that's the equation we have to solve. So the following three equations for m1, m2, m3. So number one is 0 equals minus m2 squared c squared plus 1. And this directly gives you the value of m2, which is 1 over c. Yeah, considering the positive root only. The second equation is 0 equals m1 minus m2 m3 c squared. Luckily, again, we do not need m1, so we can get rid of it. The third equation is 2m2 minus m3 squared c squared. So this can be used to find m3. So from here, you will see m3 is square root of 2m2 over c squared, which can be further, if you replace m2 as 1 over c, what you will get is 2 over c cubed, right? Or 2 over square root 2 over c square root of c. So therefore, the optimal gain vector k bar is c squared m2 m3, and if you simplify it, what you will get is c and square root of 2c, if I am doing it correctly. So c and yeah, so that's your gain vector. Okay, so that was the first step. The next part of the problem asks you to see what are the poles of the closed loop system. So if we use this controller, then the closed loop system, or the closed loop system, will be A minus BK, or will be described by, will be yeah, I mean, described by A minus BK, and A minus BK turns out to be 0, 1 minus C minus square root of 2C. Right, so if if you go to the characteristic equation route and then find the characteristic polynomial, eventually try to find the roots of the polynomial, you can say that the closed loop poles will be at S equals to C over square root of 2 minus 1 plus minus J. Okay. And again, I think you can do a analysis of how this behaves when the C gets larger or smaller. But in this case, there's nothing spectacular going to happen, simply a scale up of the pole locations. Okay, so that's the case when there was no external input A, but I will also do the second case here when A is a, so A is a non-zero constant. So if that's the case, then the state space will be will become x dot equals 0, 1, 0, 0 x plus 0, 1 u plus 0, 1 a, right, with a dot equals to 0. So that's a special way of handling constant inputs. So A is an input, but the evolution in A is not there. So the change in A is, with time is 0. Okay, so then you can expand it. You can actually, so in a compact form, the expanded state space can be written as, let's say, x1 dot, x2 dot, a dot. This is equals to, I mean, if you have to write this, basically x1 dot is simply x2 dot. So you will have a 0, 1, 0 here. And x2 dot is all zeros. So no, but x2 dot also has an a, so you will have zeros here and 1 here. And the a dot is simply 0, so there's all zeros in this row. And finally, for the input, you only have the input at the second state. So that's the B now. Okay, so cost function now is the same, but the Q and R matrices have to be redefined. So the cost function is t to infinity x1 squared plus u squared over c squared e tau. So the Q and R matrices can have to be redefined. Can be written as Q equals 1, 0, 0 and R equals 1 over c squared. Okay. So because it's a 3x3 state space now, so your Q and R should also be consistent with the dimensions. Now M bar again also has to be redefined. So let M bar be a symmetric matrix, positive semi-definite. But now again 3x3, so you will have M11, M12, M13. But because of the symmetry, you will have M12 here, M13 here. Here we have M23 and then M23 here. So that's the M bar, and the controller gain will be K bar is R inverse B transpose and M bar. So if you compute this, it will turn out to be C squared 0, 1, 0 M bar. So we only pick one of the columns. So that eventually turns out to be C squared M12, M22, M23. It's this row here. Okay, so basically we just need to figure out these three values in order to be to find the gain K. Okay, so if you go ahead and solve the Riccati equation, obviously it's a long process. I'm not going to do it because of its 3x3 nature. If you solve it, the result will be the following. So that results in K bar to be C square root of 2C and 1. Right, and the first part is from the case. You can see that if there is no A, then we just have these two entries. But when we have A, we will get this additional 1 here. So the implication of this is, so the controller will be U equals minus K bar X. So if you compute it, that becomes minus CX1 minus square root of 2CX2 and minus A. So so here we can see that we are actually rejecting the disturbance. So rejection of constant disturbance. Right? So good thing about LQR controller is if there's a constant disturbance in the system, that disturbance gets canceled out by the feedback controller. So we didn't have to go through all this procedure. We could simply find the controller without A, and at the end we can append this piece here. We can just put a minus A outside. And that probably will help you also in the homework where you may have a constant disturbance signal, and if you want to find an LQR, you can simply reject the disturbance. So initially you can assume that A equals to 0, you can solve the LQR controller, and at the end you can reject the disturbance. Okay, so just a few more comments before we go to a generalized LQR scenario. So first thing is the finite horizon problem. Can be solved in a similar fashion. Okay, except that we will need to find solutions to differential equations. Okay, so I mean, in order to do that, you can leverage computational packages like MATLAB or other solvers. Right, so when it comes to differential equations, solving them by hand is difficult, even in the most ordinary cases. So the best thing is you make use of some solvers and find the matrix M. Once the matrix M is there, then you can easily find the LQR controller. But mind you, the controller gain will be a function of time. It will not be a constant matrix or a vector. And the reason is because the solution of differential equation will be a function of time. So that makes this a dynamic controller instead of a static feedback gain controller. But I mean, this is a useful thing to know, and in your projects or other applications, when you need a finite horizon of time, you will have to use some solvers to get a optimum controller. Now, before we finish our discussion on the LQR, there's one more topic that I wanted to talk about, and that's about the generalized LQR. So up till now, we have seen a very simplified LQR where we just have the matrices Q and R, and even those are diagonalized. But in a general LQR formulation, and again, I am not going to derive everything here. I will just give you the important results. The derivations will follow a similar structure, but are more involved. So the generalized form of the cost function for an LQR controller is the following. So it's the cost function V is a cost from, or the integral from time t to time tf of x transpose qx plus u transpose ru. Or maybe I should write the cross terms first. So plus 2x transpose SU plus U transpose RU d tau. Okay, so we have seen these two terms before, but there could also be a cross term, which is a combination of effort and time. Obviously, it doesn't really make sense to multiply both of them, but in cases or for mathematical completeness, this formulation is definitely possible. And if there is a meaning to this term, then this formulation can still be used. But generally, if you just split it up into effort and time, then we simply need two quadratic forms. Okay, so if let's say you have this form of an LQR controller, then the optimal can still be obtained. So the optimal LQR controller takes the form U equals minus K hat X. And it turns out that this is R inverse B transpose M hat. That's pretty much the same, but there's an S here. So, and then there's an X. So this basically is the K hat for the generalized case. Okay, so, but another important thing is that M hat is now also slightly different. If this is the K hat for the generalized case, important to note here is where M hat is the solution to the following Riccati equation. So that equation becomes minus M hat dot equals to M hat A bar plus A bar M hat. This is transpose, and then minus M hat B or inverse B transpose M hat. I think there's a transpose somewhere. But let's see the previous formulations. Yeah, so M, oh, there's no transpose. So it's M everywhere. Okay, so this, and then there's a Q bar. And interestingly, the A bar is A minus B or inverse S. And Q bar is Q minus S transpose R inverse S. Okay, so that's the difference when it comes to a generalized form for the LQR. Okay, so now we're going to solve one more example before we complete our lecture today. And that example is, or let's call it an exercise. Probably you have an opportunity to look at it in the homework. So consider a a temperature control model which can be described by the the following set of equations. The first one is x1 dot. Oh, excuse me. X1 dot equals minus x1 plus x2 plus u, and x2 dot equals x1 minus 3x2 plus 2x x0. So x0 or xo is the outside temperature. And xo dot is 0, right? So x1, x2 are internal temperatures, and xo is the outside temperature assumed constant. And u is the control input. And when I say control input, basically because it's a temperature control system, so u positive means adding heat to the system, and u negative means removing heat. Okay, so that's the system that we're looking at. The cost function cost function can be written as j equals the integral from t to infinity c1 x1 plus c2 x2 whole squared plus k squared u squared d tau. Okay, where c1, c2, and k are positive constants. Okay, and then again, the problem statement would ask you to find the feedback controller, and the same thing for yeah, basically find the gain, feedback gain for this LQR controller. Okay, so first thing is we can again start with the case where xo is 0, and this is to simplify the derivation of the controller. Otherwise, it will be a 3 by 3 system, and then that makes it more complicated because Riccati equation will be a 3 by 3 matrix, and we will have more variables to solve for. So for now, following our previous example, we saw that if the external disturbance is a constant signal, then you could actually get rid of it and assume that it is being rejected at the output. Right? It's being rejected by the controller. Okay, so if you consider xo to be 0, the state space becomes It's x1, x2 dot equals -1 minus so -1, 1, 1 minus 3, x1, x2 plus 1, 0, u. Okay, so the first thing is to figure out what is the Q and R, right? So remember X transpose Q X is C1X1 plus C2X2 whole squared. So it turns out to be, if you simplify this, this will become C1 squared X1 squared plus C2 squared X2 squared plus 2 times C1 C2 X1 X2. Right, so basically this will say that your Q will be so your Q matrix will be C1 squared here, C1 C2 here, C1 C2, and then C2 here. Okay, and your from here directly I can say that the R is simply K squared. Okay, so we figured the Q and R matrices, and the LQR controller gain is K. Oops. So it will be K equals R inverse B transpose and M bar. Okay, and R is K squared, so that'll be 1 over K squared. And we have 1, 0, and M can be generic, M1, M2, M2, M3. So we are we're looking at something of the form 1 over K squared, M1, M2. Okay, so that's what we are looking at. Now the so the algebraic Riccati equation can be so we can express that as 0 is M bar A plus A transpose M bar plus minus M bar B R inverse B transpose M bar plus Q. Actually, we have to look at the generalized form. So let's go back to the previous case. So here our Q is not a diagonal matrix anymore. So we can see that we have a different structure here. But it doesn't have to be. So interesting thing is there is no cross term. So we are still in the same Oops, I think I missed a bracket here. Okay. Yeah. So so what we have is a cross term between x1 and x2, which is x1, x2. So therefore, Q is not a diagonal matrix, but the U and X are separated. So we don't have a matrix S, right? So S doesn't need to come in. So therefore, no generalized LQR will be needed. So we are back to the old scenario, and let's try to formulate this Riccati equation here. So zero matrix will equate to the M bar, which is the following. So matrix A is -1, 1, 1, -3 plus -1, 1, 1, -3. Which is A transpose, and then M will be the same. Minus M the B is 1, 0. R inverse is 1 over K squared, and then we have 1, 0 here. And then we have M again. Plus the last thing is Q. Q is C1 squared, C1, C2, and C2 squared. Okay, so further simplifying will give us the following. So we get M2 minus M1, M1 minus 3M2, M3 minus M2, M2 minus 3M3, plus M2 minus M1, M3 minus M2. Okay, this should be the same. So M3 minus M2, and then this will be again M3 minus M2. And then we get M2 minus 3M3 minus M1, M2, M3. And then here we get M1 over K squared. And this is M2 over K squared. And then we get I hope I'm doing this correctly. Okay, so yeah.
The third expression is already multiplied with one symmetric matrix, I think.
Which one?
The problem.
This one?
Yes. So the middle matrix.
Yeah.
It's already multiplied with the one of the matrix.
Okay, this is multiplied already?
Yeah. I think.
Oh, yeah. Okay, so I think I don't need this. Yeah, I was thinking there's a mistake somewhere. Okay, so this is C1 squared, C1, C2. Okay, so then if you simplify this, then we get 2M2 minus 2M1, M1 minus 4M2 plus M3. And then we get 2m2 minus 6m3. Okay, and then here we have 1 over, so it's m1 squared over k squared, m1, m2 over k squared, m1, m2 over k squared, m2 squared over k squared, plus c1 squared, c1, c2, c1, c2, and c2 squared. Okay, so we are left with I think it's going to be a complicated problem. So first one is 2m2 minus 2m1 minus 1 over k squared, m1 squared plus c1 squared. Okay, so that's an equation in m1 and m2. Second one is m1 minus 4m2 plus m3 minus 1 over k squared, m1, m2 plus c1, c2. Third one will be 2m2 minus 6m3 minus 1 over k squared, m2 squared plus c2 squared. So we have to find m1 and m2, but we've got two equations that have m3. So I'm thinking from 2 we get m3 equals 4m2 plus m1 m2 over k squared minus m1 minus c1 c2, and we can substitute into 3. So now the difficulty starts. So 2m2 minus 6, and then this whole expression. Okay, then 1 over k squared m2 squared plus c2 squared equals 0. Now we've got m1 and m2 here. So all right. Okay, so let's simplify this. Minus 6m1 m2 over k squared plus 6m1 plus 6 c1 c2 minus m2 squared over k squared plus c2 squared is 0. So we further simplify this, it's going to be minus 22 m2 minus 6 m1 m2 over k squared plus 6 m1 plus minus m2 squared okay, plus 6 c1 c2 minus m2 squared over k squared plus c2 squared. Okay, that's where we end. So from equation 1, basically m2 can be substitute m2 or m1, any of the, no, actually m2. So m2 can be m1 plus m1 squared over 2k squared minus c1 squared over 2. Okay, which we can substitute in 3. So I think it's going to get a little messy. I'm not sure if I'm making mistakes here, but this is included as part of the homework, so you can solve it in a cleaner way. If you substitute this in minus 22 m2, it will be m1 plus m1 squared minus 6m1 over k squared m1 plus m1 squared over 2k squared minus c1 squared over 2 plus 6m1 minus 1 over k squared m1 plus m1 squared over 2k squared minus c1 squared over 2 whole squared plus c2 squared plus 6c1 c2 equals 0. So you see it's getting a little messy, and but at least the thing is we have a quadratic equation in m1 from which m1 can be found, but we just have to simplify these constants a little bit. So it will be minus 22 m1 minus 11 m1 square over k squared minus 6 over k squared m1 squared minus 3 over k squared m1 squared plus 3 over k squared c1 squared plus 6m1 minus 1 over k squared m1 squared plus m1 to the power 4. Okay, so there's the power 4 plus c1 to the power 4 divided by 4 plus 2m1 cubed 2k squared minus m1 squared c1 squared over 2k squared minus m1 c1 squared plus c2 squared plus 6 c1 c2. So this is just my simplification, but I don't know if there's a mistake or not. But since this is a homework problem as well, you can actually try out the solution at home. So eventually we will get a solution to the values for m1 and m2. C1 squared over 2k 4 minus 1 over k4 minus m1 to the power 4 divided by 4k to the power 6 plus 11 c squared plus 3 over k squared c1 squared minus c1 to the power 4 plus 6 c1 c2. So I think I might have made a mistake somewhere leading to a complicated expression, but eventually the goal is to solve for m1 and m2. I will clean this up and write it in the notes that are published, so you have the right version. But obviously this is again the first part of the homework, so you will have also the opportunity to try it out and make sure there's no error that was made. And eventually the second part is if we assume that your XO is not 0, then you can actually leverage the disturbance rejection property of the LQR controller. So if there is an external input which is constant, it can actually appear as minus 2x0 in the gain. So your K will have, or your U equals to minus KX, right? Will have the minus KX without x0, and then you will also have minus 2x0. So hopefully this controller, the U will actually compensate for the x0 which is appearing in the system. But you have to try it out. You have to solve this with an augmented system and see whether the 2x0 appears at the output or not, or whether the disturbance is being rejected or not. So so I'm going to clean this up, the write-up a little bit before publishing it, because I think there must be a small mistakes in somewhere in the in this piece here, which has made the that has made the solution a little bit tedious. I think it's not that complicated, but you guys can also give a try and also solve the homework. Okay, so after this LQR controller, we are going to also look at another type of controller in the course. That's going to be so that's going to be a linear quadratic Gaussian controllers. This is again, this is linear quadratic for the same reasons. This here is a Gaussian noise. So eventually we are looking at a system with some added noise. So if x dot equals to ax plus bu plus some v, and v is some Gaussian noise, then the optimal gain controller that minimize a cost function and also takes care of the Gaussian noise is called an LQG controller. Right, so remember this, I mean, if the system is this piece here, we will say it's an LQR. If it's considering this larger piece, it's an LQG controller. Right, so that's going to be a topic for next time, next lecture. But beyond that, what is important to understand is if the state variable is not observed or is not known, which is generally the case, we will have to estimate the state, right? So so LQR and LQG are use a state feedback control law, which is U equals to minus KX, right? And again, assumes that X is known, which is not the case. So if X is unknown, we have to construct an estimator for it, and the optimal state estimator is okay, also under, so optimal state estimator under Gaussian noise is called, and it's called a Kalman filter. Okay, so that's going to be coming up once we get through the LQG controllers and of things of that sort. So pretty much that's the end of our lecture today. I think we've covered the LQR. We've seen a couple of examples. The last example has been a little tedious. I think there's some error there, but you can figure it out in the homework. So homework 5 has already been uploaded. So you guys can take a look, and that will be due next week. And also next week is your project mid-review report. So I hope you guys are making progress on your projects, and whatever you have, I think best to submit it so that I can take a look and get back to you in a timely manner. Otherwise, you don't have a chance to get feedback, and eventually you may have a very bad evaluation. So if there's something which is obviously objectionable, I will tell you in time. So I would say make use of the opportunity. There's nothing to be afraid of. There's no grading here. It's just for me to understand your progress, and also for you to stay on track. So I look forward to the project reports next week. Is there any questions that you have for this course or for this lecture, or anything else? No questions? Okay. Then let's meet next week. And meanwhile, if you have something to talk about, you can send me an email, or you can visit my office if I'm there. Okay. All right, then let's see you next week.
Thank you, Professor.
Thank you, Professor.
Sure. Thank you.